Okay, we're gonna go to the last part of chapter 16. You have to take chapter 16 slowly because it's a huge chapter, but then we can waive it because it's very important to you, especially in industries, because a lot of us go on optics, yeah? Okay, it's the optical polygons and we use for angles measurement. So the alignment telescope, we can use it, okay, with the optical polygons. It's just a part inside of this telescope, okay? Why do we have to do this? It's in order for us to be able to measure the angles, okay, most accurately. Alright, so optical polygons, they're just polygons. And since they're polygons, they definitely have a number of phases. So that's your geometry, okay, review from your middle school or high school probably. And they're used as standards. Alright, so there are steel optical polygons below. So this one and this one is a glass with metal enclosures to protect them, and they have openings, alright, at the faces. So here they have openings right there. So anyway, no need to go into details for that, and if you can't be able to understand an optical polygon looks like this, and we use it or inside of the telescope, alignment telescope, to measure the angle, that's good, right? At least you have to remember that much. Functional, right? The picture is not very good because it's really blue and difficult to see, differentiate the steel from the glass. Anyway, no need to remember the details of the instrument. So where we're going to use it, so they're used as standards, again for calibration for our instruments, and we use it for certain machines, 2 angles, and that's the normal use. Rotary table calibrations. So rotary table, we use them for calibration with your optical polygons. So with the table at 0, the reflected, why? Because with the table at 0, okay, this rotary table, we're going to set it at 0. Why? Because we're doing calibration. Every time we're doing calibration, you should know by now we're setting it 0, yeah? And the reflected image of the cross line, since we're dealing with the optics, you always have a reflected image. So that reflected image of the cross line is first set at 4 degrees, alright? Then it is rotated 135, and then we rotate it again to 225. So here for 0 set, turn it, alright, even if it's 0 sets, about like the very first one is like about 4 degree angle, right? And then we go 135, and then we go 225, and that's what we do in calibration. Again, you don't have to know the numbers, you don't have to get into details. All you have to know is the procedure, okay, how we're doing it. First, try to set the instrument 0. That's your rotary table, right? Then the reflected image is at 4 degree angle. Then we're going to rotate 135, and then we're going to rotate again to 225, right? And that's what we're doing. So here it just is showing you the corresponding, alright, scale right here is just moving. Look at that, yeah? It's going movement, you can see. The movements is depending on, right, the calibration, again, on the angle changes, yeah? Because we're dealing with the angles anyway here. Okay, so here you can see in this picture, right, that's the same, but it's a little bit deviated from the previous picture. But so if greater deviation, right, than 3 degrees is discovered, meaning like we started out our reflected image at 4 degrees. So if we have like 3 degrees, all right, spacer or shims, okay, we use them to correct it until that deviation is within 3 degrees, alright, of all checkpoints. So the very first one, remember the reflected is 4 degrees, and then we turn 135, and then we turn 225. So where's my cursor? So you started with 4 degrees, okay? And if you have like a greater deviation than 3 degrees, So let's say if you add another some more, okay, 4 degrees, so you're gonna have a total of 8 degree. That is, alright, greater than 3 degree deviation, right? And at that time, we're gonna use a spacer or shims to correct that, okay? So the same thing, 135, if you have a floor, okay, more than 3 degree, you would have gotten it's like 139 or something like that. In that case, again, we use a spacer or the shims to correct it. And then you have to check, alright, all the deviation, and that's got to be within 3 degree. Or 3 checkpoints. So the checkpoints are at 4 degree, at 135, and 225. So you can go as far as +3. Okay, you can't go more than that for deviation. So this here you can go 228, you can go 138, and then you can go 7 here, yeah, for your reflected image. Alright, then angle readings are taken. Our purpose using this optics is to read the angle. Alright, in part 3. So angle readings are taken. They're starting from your 0 phase and then go 45 degree intervals all the way to 350 degree. So what we're doing right here is, alright, in A reading is taken for the 0 phase, yeah, 0 phase, and then the table is going to be rotated, and then in B right here a reading is taken, okay, from the 45 degree, okay, 45 degree right here face. And it would be very difficult for you to be able to see it because here I can point that out for you. So this little one, alright, that's this one, yeah. So now angle is right here, okay, directly connected to your instrument, so you can see right there, and that's your 0, okay. Scan, this is your data reader right there, your knots, and right here is your angle right there, okay. So when you carefully look at it, I suggest you use a handout and you can zoom it in, alright, and you can go from 100% all the way to 130, and you're going to see right here that's 45 right there, okay, this little number right there, that's a 45. So you start with 0, then go to 45, and then you're going to go intervals all the way and go one round for 360 degree in the rotation, yeah, so that way you're going. So 0, and then 45, and then 90, okay, and then go all the way to 360 degree. In some of my recording, for some reason, I think when they make the video in PowerPoint, the pointer dropped and it's not coming up. So anyway, if you can see my pointer, that means it's just compressed or damaged, data damage on the way. Okay, so in this table, we're just showing you the readings. Okay, here they enter into a chart like this, and they're corrected to the errors. So when you look at the column 7 right here with a little star right there, so you can see the corrections. Okay, for your polygon errors, this is your polygon, okay, optics. And then note, you can see up and down here, up and then here down, and that's just referring to increasing, alright, and decreasing angles respectively. Since we're using the angles, your units are degree, units are seconds, alright, but its angle is nothing but an arc. So make sure you review your physics, right? Arc is like that. I don't have a perfect circle here, but that's a circle, alright? So this is your angle. The angle is, we call it A, and then R, C, okay, arc. This should be A, it's not Q. So anyway, so therefore we use degree, and then we use second, okay? Don't confuse with time. This is angle for this chapter. Although sometimes I wonder, like, like how the high school teachers are teaching you guys. Some of the students just don't know what is what. They just have no idea what is a unit and which one is what unit. You better review your physics, your chemistry, and your biology. And I strongly suggest that you don't be stingy. Okay, you have to know that foundation. Your biology 1 and 2, physics 1 and 2, and chemistry 1 and 2. Okay, if you have like more money and time, make sure you get these foundations, because the natural sciences are what we have here and they're all connected and we are a part of it. Okay, and you have to understand these foundations so you can be able to do applications. Otherwise you will be losing you will be having a lot of gaps in your knowledge, okay, so that you can't connect the theories and concepts easily. So if you have your foundation real straight, it's easier to connect and apply, all right, between subjects. All right, the next one is we're getting into two-polygon. We're going to use two polygons instead of one in the previous calibration, and we will do calibration, right? So polygons, you can add it some more and then you can subtract it, because they're just we're in the optics, so they're just kind of optics or mirrors, okay? And you can say mirror prisms. So, and they come in all shapes, okay? And we're dealing with the lights, okay? Lights can reflect on a surface, so therefore we are playing with the surfaces, different surfaces, and the light, okay? So humans are very intelligent. Education is not equal to intelligence. Education and intelligence are totally separate things, okay? So don't confuse between the two things. Education is more of a wisdom, right? Trying to differentiate between right and wrong and try to come up with the best possible choice in a particular situation. Intelligence is you can apply, and it's also positive and negative. So you have a negatively smart and you have a positively smart, okay, intelligence. And you don't need education for you to be intelligent at all, okay? Those are two different things. Don't confuse. Alright, so anyways, get back to calibration. So we're gonna get back to this all rotary table. Right here. And then can be done with gonna do with two polygons this time. Yeah. So instead of using 72 phase polygon, we're gonna use 8 phase, and then we're gonna use 9 phase polygons. Yeah. So it doesn't have to, even though we see like polygons, it can be many different phases. Yeah. So here, one polygon, you have 72 phases. So that's like a 360 degree divided by 72 phases. So therefore, each phase is going to give you 5-degree calibration. So two polygons, we're going to use 8 phases. So you have 360 divided by 8 phases. So each phase is going to give you 45 degree. Alright, for 9 phases, you do the same thing. Divide 360 by 9. Alright, you're going to get 40 degree. Okay, so and then you're going to subtract that 40 degree from 45. So you're going to get the same 5-degree calibration. Okay, so instead of using the entire 72 phases polygon, you can break it into two polygons. One is 8 phase and the second one is a 9 phase. How do we calculate the calibration angle? All we have to do is just use our total angle 360 divided by the phases, and you're going to get your angle. Okay, so and then you're going to subtract that because you're using two of them, so it's going to give you the same 5-degree calibration. So therefore 72 phases can be broken down into 8 phases and 9. Okay, and then how do we decide what phases to use equivalent to 72? You have to do a backtracking, okay? So in order for you to get the 5-degree, you can subtract 45 degree, all right, and minus 40, okay? You can also subtract 35 degree, all right, minus 30, and then you have to walk away all around, okay, all around to 360 degree. But this is going to give you the most logical thing, because if you go with 35 minus, all right, 30 will give you 5-degree calibration, but then it won't go all the way around for 360. Okay, so nobody is asking you to do this kind of calculation at all. You just know that in here for this assign, I mean not for this handout, okay, text in this chapter 16, all you have to know is you don't have to use just one single polygon, right, with a number of faces. You can break it down into two polygons, right, with different faces. And then we can be able to calculate the same degree calibration. That's all you need to know. So don't get frustrated into calculation. That's just a engineering part and a whole brand new course for you. So calibration of two 12-sided optical polygons. So here we have 12 sides with auto collimator. That's what we're using for instruments. So here optical polygons are also calibrated to ensure the angular measurement, the precision, right? We have to do calibration. Every time we do calibration, what are we doing? You make sure that your instrument, is going to give you accuracy and precision when you use it to measure it. So then, deviations among all the faces, are measured. Errors are in the measurement of the angle. Errors are in the instrument, in the procedure of the measurement. So here errors are in the measurement of the angle and in the reference. Alright. So this error is found by averaging the measured deviations. Okay. You always have to do the average if you have different data. Okay, if you have like only one single data, then you don't have to do average. Okay, so when you look into this columns right here, you have 1 all the way to 6. Okay, so the readings between the pairs of the faces are in the recorded differences. So that's in the column right here. Okay, so here this is your recorded differences. Yeah, since it is the differences, that's the reading between the pair of faces. Yeah, and the deviation from the reference is going to be your column 4, which is this deviation from reference, how far away, right, your data is from your reference. So that's your second of arc. Again, that's just the unit to measure angle. Okay. For example, let's say 6.5 minus 6.3. 6.5 minus 6.3 is going to give you and then plus 1.5 is going to give you minus 1.7. So I'm going to write that down for you. Okay, here I'm going to get this, and then I'm going to draw this out for you here so you can see, alright, an example. So here we're going to take 6.5, which is this one, okay, and then minus 6.3, which is that one. Okay, and then we're going to add, this is minus 1.5, because that's the deviation. So this is the two data, okay, and then we're going to get minus 1.7. So this is how we calculate one by one. So here in this case, the same thing, 8.0 minus 7.1, okay, and then minus 0 is going to give you minus 0.5. 7.1 minus 6.5, alright, so here I can write that down for you how we calculate that two column, right, minus, and then 6.5 is going to give you, and then you're going to add minus 0.9, okay, 0.9, and that is going to give you minus 1.5, okay, so that's how we do calculation between the recorded differences and deviation from the reference. So and then you go all the way down, and the last one is you will get minus 8.4 deviation from the reference. So if I give you assignment for this, so you can be able to do it, okay? Okay, so that way we can measure all the differences between these faces. But there's still the error in the initial measurement, okay? Face number 1 to face number 2. So that's between this and this. So here altogether all faces, because it said that's a 12-sided optical polygon, so therefore we have 1, 2, 3 all the way to 12 total, yeah? And then now you get idea of how we carry the deviations, alright, into all the subsequent measurements. So this is compensated for by averaging again all the deviations, right? So when you take a look at this little note right there, okay, see the note at the bottom of this chart right there, we see the correction factor we're using here, so minus 0.7, alright, times minus 8.4 divided by our total 12. When subtracting, adding algebraically, subtraction is nothing but just algebra, and you should know that from your middle school math. And for measured deviation, so column 4 and then column 5. Okay, so the results are the true deviations, which is this one, column 6. So because the circle must have a 360 degree, so the test is that the summation of deviation equals to 0. So here you don't have to know that details, alright? All here, when you look at the column 6, that's your true deviation. So how do we calculate it? It's just this, alright, minus that. Okay, that's it. So sorry, this minus that. So that's it. So when you go, I'm gonna write this down for you. So we have a column 4, okay, minus the 0.7. Because this table, they reverse the column 4 and 5. It's a little bit difficult to see. And then so you're gonna get that one. Usually this one is on the side. Anyways, it's okay. So deviation from reference, okay, minus correction factor. Alright, they are all in second unit here plus second, which is little s. Okay, if you want to write it like that. You're going to subtract 5 from 4, okay, column 5 from column 4, and you'll get each one of them. So here, so minus 0.9 and then minus 0.7 will give you minus 0.2, okay. Here minus 1.5, okay, you write it this way, and then minus 0.7, okay, it's going to give you minus 0.8. This is very difficult for me to write here. So anyway, so you got it. So it's not giving me. Okay, got to trying to erase that. Really difficult to write. So anyway, so you get minus 0. And then 8 right there, which is here. And so you calculate all the way down. Yeah. Okay, so let's get into JIG Transit. That's just the planes. So JIG Transit is an instrument and also called Optical Transit Square. Okay, Transit Square, we also call JIG level, but most of the time they call it JIG Transit. And it's used to establish precise, again, vertical planes and then plumb line. Okay, this is just a term, comes with it. So it looks much like the surveyor's transit. Okay, the people who are doing the survey. So if you go to engineering department, usually they have to do the survey. Okay, something to either measure the building or measure the field or stadium or something that the professor's going to send them to with the instrument to do that. Usually laser, I believe, on what I've done before. So anyway, so our department, we don't have it, but then in the future, like I said, we're going to develop this course, okay, to the next level. So at that time, we're going to be having different instruments for metrology measurements. So it looks much like the surveyor transit, and we call that JIG transit. So a right angle eyepiece, okay, we're going to use it to establish, okay, the zenith sight, just a point directly above the point of reference. At infinity, okay, it can be added without auto collimator and projectors. Every time you're dealing with optics, you have to understand infinity. You really have to understand how the light is going, how the light is reflecting, how the light is moving, okay? And what can we do about it by using mirrors and prisms? So when you look at it right here before tilt is corrected, okay, this is after tilt is corrected, all different. You can see the crosswell, like cross, okay, line right here. it's completely aligned here. Okay, here you can see the deviations. So dotted lines are reflected, cross lines. Now here these are your dotted lines. So these are just for the reflected images. And then here, see our original crosshair is completely lined. Okay, after the tilt. So what are you tilting? You're tilting your JIG transit. So the radical pattern, okay, radical is nothing but this. You can see this view, and you should be able to see this by now, okay, after part 1 and 2. So the radical pattern for the JIG transit, typically it's just a cross pattern type, okay, but with paired lines, because you have paired lines right there in the 2 quadrant instead of our regular, yeah, instead of our regular thing right there, you have a paired line. So that's what we're talking about. Okay, so here you can see that, and here you can also see that. So pair lines are in the 2 here. You can see your quadrants right there. So you can see the pair line in 2 quadrants, and a single line in the other 2 quadrants. So the single line is right here, right here, right here, right there. So 2 quadrants, that's 2 quadrants. Here, that's 2 quadrants. And then that is your 2 quadrants. Quadrants are nothing but here, see? 1, 2, 3, 4 quadrants right there. So you can draw this one. Okay, another crosshair right there, and you can be able to see these quadrants. I can do that for you here, so you can draw that way. See, like how they're in like 2 quadrants for single line and a pair line. So I'm gonna erase that now. Back to my laser. Okay, so the broken lines are these ones. Okay, show how this appears when used with autocollimator. So again, don't stretch yourself out. Remember, we're dealing with the JIG transit. Okay, and we call that different names. Okay, and we use it to establish planes, right? Vertical usually. And then they're pretty much like the severe transit. Now we have a point, and that's called zenith sights. That's directly above the point of reference, and our reference is always at infinity for this type of instruments. And you can use this one with the autocollimator and a projector. Okay, so with a JIG transit, you can see all 3 axes right there, okay, intersect. And the rotation again is possible. 2 of the axes. In case when you look at it, you cannot be able to see right now. So after you finish your 3D courses, you can be able to see these axes very clearly. So every time you rotate, then you can see that here is a 1 and here is a 2 rotation, yeah? And that is happening in 2 axes. Okay, just go slowly and go carefully. And make sure you know what you're looking. Okay, so if you put consciousness in what you're seeing, then you know what you're looking. Yeah. If you're just reading blah blah blah, then you can't be able to see it. So make sure you go slowly and carefully to read and be able to see these axes and then the angle of rotation. So here you can see your vertical, and this is your optical axis because all your optics are right in that line. Okay, and then this is your horizontal, so that's X and that's Y, and then this is your Z, yeah? And here we can do the rotation because it's an instrument and it's on the pads right there, okay? And you can be able to rotate that base. So here the geometry of your JIG transit can rotate. Again, this is in a circle, so every time you have a circle here, you can be able to rotate 360 degrees around, okay? Either clockwise or anti-clockwise, whichever way you want to go in vertical planes. Alright, so the next one is your cross-axis feature. So here you can see the cross-axis feature is like it's really important feature in JIG transit, right? So this little thing that you saw, so that one, okay, and you can also, okay, we already look at a new base, and then there's your instrument, and then we have our axis right there if you remember the previous. Alright, pitch hole. So we're gonna take a look at that cross-axis. So this feature is gonna let two perpendicular lines, okay, of sight intersect on the azimuth again of the instrument. So don't forget what azimuth is, right? And then along this axis, your telescope, all right, axial mirror or telescope, you can add it, all right? So that's why this feature is very important, because we can be able to do the attachment on it. Okay, and so here, this is just a exaggerated picture. So when a telescope is built, right, it's called a JIG Transit telescope square. So when we talk about telescope, don't think about like a big telescope to look at the stars and planet, alright? That's also a part of it. We're talking about the metrology telescope that we use here in the world, okay? So it's called the JIG Transit telescope square. How can I say the simplest one? Okay, simplest, alright, optics metrology. You can get it from Home Depot or Lowe's, okay, home improvement, whatever, go there. You're gonna get the laser, alright, okay, laser measurement tape instead of a regular, okay, that you use with this long. You have to pull it out from here. We don't have to do this anymore. This is deprecated, but then still people are using it, so you can still find it at Home Depot and Lowe's. But then optics are now okay used. So you also have like laser instruments that you can be able to send the laser, so you can be able to get that measurement without pulling this long tape around. So anyways, let's go back to this telescope. So again, cross-axis. Alright, telescope has again infinity focus and a cross-line pattern. Alright, reticle. So the one that I draw for you, this little one, don't forget it. So that's our reticle, and that's our cross-line pattern. So that's what we can be able to see in a cross-axis telescope, because they have infinity focus. Okay. Alright, so when you look at this picture, so let me clear this out of my mess here. Okay, here we go. I always forget this laser pointer. So when you look at it here, the two lines of sight here and then here, okay, they intersect. But they do not optically interact. So interaction and intersection, the lines are intersecting. So these are all just imaginary lines, while your instrument is building along these lines, okay, so that you can get your alignment totally correct. And however, you have your optical, okay, optically they're not interacting each other. So here's your mirror, 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 mirror. So everything is aligned in this across lines right there. Okay, you can see all the mirrors. So these are all prism. We call the P R I K S M. They come in all different shapes. Some are triangle, some of them are convex, okay, some of them are concave, like this. Depends on where you want to direct your light, okay, and how much angle you want it. So I'm going to erase the skin. Oh, right, it's really hard. Okay. Okay, so when you go back here, you can see here this is your feature, right? Main telescope. That's your covering, and that's your eyepiece. Alright, this is your reticle adjusting screw, so where we can be able to see the cross line right there, and then the cross axis line of sight. Okay, is right here. And here's another axis right there. Then we go into leveling. So leveling is also very important because the circular level, right, called bullseye level is used first, and then the four leveling screws are adjusted. And we're talking about this base right there. So why do we need to do the level? Because we want these, okay, line of sight, and then these vertical, okay, axis, and your z-axis to be all perfectly aligned. So therefore you have to use the pads, you have to use the screws, okay, to adjust to get this alignment. Application, how are we going to use it? Applying. So some students ask application, okay, real life. I tell you again and again is you've got to learn, right? First the theory, second you have to get these theories in your head. So once you get that, you can be able to apply by using your intelligence. So this is where the separation of education, okay, and intelligence is just right there. Education is just getting knowledge and information, and then we practice many different situations and problems and issues for us to be able to come up with the right, okay, decisions and to separate right from wrong. And then if we don't have right or wrong, to come up with the best possible solution, okay, out of what we have. Now that's education. Intelligence coming out the bridge between the education and application. Okay, when you talk about application to apply in the real life, there we go. That application got to do with your intelligence. Okay, that I can't give it to you because that is in you by yourself. You have to find out how you work with your brain. And if it's not very developed in you, you have to practice. Okay, repetition, practice is going to train your brain to be able to think, okay, in a correct direction so that you can be able to do application. So therefore, people who can't be able to bridge the education, knowledge, concept, and theory to application by using intelligence got to be trained again and again, okay? But they need somebody to guide them because they can't do it by themselves. But when you come to university, all the professors from all different subjects are trying to teach you, okay, to use the intelligence you have to be able to apply your education in the real life, okay? Otherwise, only professor will become better and better because they got to do everything that you're supposed to be doing repetitively, okay? So make sure you attempt, okay? You attempt to do that. And I suggested it, practice it from your home, okay? What you have first before you get into all your career, yeah? Okay, so now let's get back to JIG Transit application. How are we going to use that? So when you take a look at it here, okay, it is used in to establish lines, okay, and the planes. So here we have axis, and then we're going to establish the planes, okay, by using this instrument right here. And then by using that, we can be able to take the measurements, okay, you're in metrology, taking the measurements, different kinds of measurements. So here, we're taking the measurement of the planes. So how are you going to take the measurement of the planes? We're going to use this. Okay, we're going to use the light. We're going to use the optics. And we're going to use a directed reflection of these lights to capture that measurement, okay, of the plane. So take from them and use them for alignment references, okay? So in construction, we'll be using all kinds of stuff, but the development is completely linked to online because these are industrial equipment, okay? So industrial technologies got to develop these things, all right, for the consumers to use them, yeah? So that's a hidden line that most of the students cannot be able to see, okay? So if you practice, you can be able to use it, okay? So this is how we study, okay, the things that you think like we can't be able to do it, but you can, okay, by bridging the education with intelligence so you can apply these concepts in the real world. Alright, so next one. So for large number of measurements, you have to do the measurement again and again and again and again. So number of measurements you're doing. So the station plane is established, alright, parallel to the plane of the features. So either auto-reflection or auto-collimation, we use it, one of them, to establish a, again, line of sight at 90 degree to the station plane, okay? 90 degrees is a square, okay, it's a perfect angle. So every time we do a plane measurement, you have to bring 90 degree. So by means of auto reflection or auto collimation, okay, a plane right here at 90 degree, you can see the angles right there, all 90 perfectly. To the measurement, again, reference, this is our measurement reference plane right there, okay, can be created. Yeah, so that's how we measure. You need to have a 90 degree in order for you to be able to study and measure the plane. Okay, plane is right on this wall right there. And we're using the JIG Transit okay, and with our line of sight right here, okay, that's our reference plane. And then we're gonna straight this, okay, vertical line, that's your vertical axis up, all right, by using different prism right there, okay, mirrors right there, you can call it mirrors right there. And then we're going to use the light, okay, to get that measurement of this plane, okay. All right, so getting into features. So right here, if features and reference areas are in the same plane, if we are on the same plane, parallel to the station plane, the accuracy of the results is increased. Okay, don't try to stretch yourself out trying to look at it. Just try to understand that you have your plane. Okay, I'm gonna just show that. Where's my pen? So you have your plane that you're trying to measure with your instrument. Okay, so the features and the reference areas are in the same plane. So your reference area, okay, and then the one that you are measuring the feature, if they're in the same plane, your accuracy is better, yeah. Okay, so when you take a look at it, in this exaggerated picture right here, this is just showing you a diagram, okay, the way a line of sight can be created 90 degree right there. So here's our instrument, okay, here's our mirror right there, here's the station plane that we're trying to measure. So 90 degree is we're creating with this mirror using it, and then here's our auto reflection target right there. It is automatically reflecting what are we reflecting? The light rays, okay, coming into this mirror. And this is our LOS right there, line of sight, okay. You have to get this thing perfectly horizontally 90 degree to your plane, and this is how we create it, by using this instrument and using that instrument together, okay. So the bottom drawings right here, it's just showing you the way the reticle, so that's our reticle right here with your crosshair that you can see, okay, reticle pattern that we can see right there, okay, and the target brought into the coincidence right here. So we're going to bring this to our crosshair, so here you can get your coincidence, that's just, in other words, it's overlapped, okay, the crosshair is not overlapped on your target, so that's your reflection of your telescope, all right, target right there. And then this is your reticle pattern. So when you see this one, all right, you have to turn the JIG Transit, all right, to overlap your target together. It's just adjusting. We call that adjusting by using these knots. Okay, so now getting into alignment. So alignment can be more difficult than measurement in JIG Transit, because alignment is it takes some time, okay, for you to align everything correctly. So for example, alignment of, in this example, we're doing rollers, yeah, large process industry machinery and paper mills right there, okay. And alignment telescope and targets are used to optically level the lines, okay. Alignment is nothing but we're leveling. You have to level something. So here we're dealing with the beams, all right, like beams. So it's got to be the lines to make them parallel in a vertical plane and then perpendicular, right, to the axis of the rollers. So here, these are your axes of the roller. Okay, right here you can see 1, 2, 3 instrument, because we have 1, 2, 3 rollers right there in our paper mills, and we're trying to align them. So the position of these rollers are important for the production of whatever they are producing, okay. So therefore industrial metrology is this, and industrial technology is you, okay, got to do this job, okay. So here when you take a look at this picture, so the alignment of rollers right here, okay, in a large process machinery, but they're pretty big rollers. It can be difficult, right? You gotta go and stand up with user support to be able to do the alignment. So no mechanical method can compare with the ease and reliability, okay, of optical alignment. And here it is showing you one of the several methods that can be done, and you have to use each JIG Transit for each roller here to get the alignment straight. So why do we need the alignment? Because you are in a process industry, okay, industrial machinery, and we're not, in this case, is in paper mill. Alright, support. So the next thing you have to know about this instrument is the support. So practically the supports are very important again for optical instruments, right? Linked to alignment again, because they provide a quick also setup. Yeah, so if we're doing alignment, you need a quick setup. You can just set up again and again and again and again to find that alignment. So therefore the supports are very important to be able to get a quick setup, right? So alignment bars, added scales to measure linear dimensions correctly. So here, 1, okay, here, 2, 3, 4, and then 5 right there, and 6 right here, yeah? So these are all we're trying to align to this structure right here. So using the standard support, so here you can see the support right here, support, and then the support. Okay, so using these standard supports facilities, optical, okay, facilitates your optical alignment and the measurement. So here this guy is trying to measure by using many different JIG Transit to get this structure, right? Okay, so telescope can be turned down, alright? Oh, here's my telescope. Okay, so telescope, there are two of them here. So can be turned downward to read the scales. So reading downward easier, okay, alright, in the optical square. So the optical square, you have already studied that in previous parts, and so particularly useful for direct linear measurement like this, alright, using the alignment bar here. So here you can see the support. Okay, and here we're putting this one first telescope right there, and then we have our optical square right here. Yeah, then you can read downward, and then this one's a baseline telescope. Another one here. This is your support. Yeah. So with this support, you can be able to turn alright the telescope downwards to read the scales. Alright, now we're getting into theodolite. Okay, theodolites, we use them for angles and planes. Okay, and you can see these instruments outside in some of the industries. So theodolite is basically just a JIG transit, alright, but we have graduated scales in it. And then we use that to measure the angles again around vertical and horizontal axis. So theodolite is used, okay, for these things when greater accuracy of your angular measurement than of linear measurement is needed. Right, angles. Here's your key point. So several angles around a single point of measure. Angles, okay, another key point. So both horizontal and vertical angles, another one established simultaneously at the same time. And then large angles or measure angles or hitting angles in play. Angular measurement is taken at a distance from a reference line, again angle. Features are difficult to be reached by mechanical means because of obstruction, alright? Because we're using the lights anyway. Construction. So the resemble JIG Transit, right? Enclosed circular scale is read by using with doing attachment, so micrometer microscope. And then gravity provides again your zenith reference, and then some use a pendulum, alright, to automatically reference the axis. Alright, circles. So theodolite circles, they're typically graduated to 1/3 degree. You just go or light on these, or just read. So you have a micrometer microscope. Right, micrometer microscope is just a microscope with attachment micrometer, so you can be able to do the readings and measurements. It's going to read to the nearest second of arc, okay, that's your just a unit for your angle, and then graduations of your circles read continuously again clockwise, alright, from 0 to 360 degrees that way. Application. Alright, so theodolites are used for all applications of JIG Transit, or measuring planes and angles and angular measurements. So they make measurements that combine the best features of optical alignment instruments and coordinate measurement machines, alright? So that's what we use the theodolites for. So beyond vision, so optical measurement depends again on our human eye. Human eye has a lot of limitation, yeah. So human eyes are also its greatest limitation. So the eye's effectiveness is affected by the measurement decision of the observer. Okay, so how this observer is seeing, all right, it's going to give you your precision and accuracy of using these theodolites. Yeah, I'm going to erase that. Okay, coming into interferometer. The pointing interferometer, we use it as again just attachment, alright, mounted on an alignment telescope to measure very small angle displacement. So inside this attachment, we use a prism, alright, device a light beam. Every time we use a prism, we're breaking the lights anyway. So if you have a prism of some sort, okay, I'm trying to draw convex, you're breaking, okay, the lights, okay, passing through that. And so that review your physics into two parts again, which are then directed at an external, alright, mirror. And then so mirror is nothing but trapping the light coming out from the prism back into where you want it to go. So the mirror returns the beams, and then the prism is going to recombine them. And then when the parts are nearly equal in length, alright, interference fringes, alright, you can see that in the eyepiece. Remember the fringes, the dark little shapes that you can see, right, in your eyepiece. And you count them for your measurement. Photoelectric instruments. Alright, photoelectric sensor. Sensors is not so popular and you're using everywhere because it's a very useful and convenient, and added to again autocollimator because they have great sensitivity. Okay, so it takes less skill to operate photoelectric autocollimators. The sensor is doing all your work. So the two primary roles for photoelectric instruments are these things. So the first one is the elimination of most eye fatigue, right? So because we're humans, so every time you have to use your eye, you got tired. So that's what I suggest, right, students to use a little towel, okay, hand towel, and then you're gonna wet it with some water, right? So every 3 to 4 hours. That's what I do because we have to use eyes a lot on the screen. So screen time every day is very okay, heavy. So you use a little towel, wet it with some water, and then put it on your eyes. Okay, about 1 or 2 minutes. It's going to get rid of all that eye fatigue. So do that every 3 or 4 intervals. All right. Your eyes also need moisture. So water is actually okay. It's cheaper. Also, it's better than buying your eye drops. Okay, from CVS or wherever, Walgreens, whatever. So eye drops, you have to pay money, and then that contains acid. So over time, even if it clears the dirt in your eyes right away, over time the usage of your eye drop is going to kill your eyes. All right. So make sure you use pure water. Yeah, and every 3 to 4 hours, when you have to use your eye a lot, okay, students, professor, we have to use eyes a lot, and our eyes are always at the screen, right? So make sure you do that, okay? If you don't want to do it, it's okay anyway. You know, it's just a suggestion because it works with me, okay? All right, the next one is okay, going back to the first one, so elimination of most eye fatigue from conventional instruments, which allows repetitive measurements without risking additional reading errors. So if you have eye fatigue, you are more likely to read, okay, wrong stuff. So therefore, in order to reduce the reading errors, all right, we use them. Another one, providing a practical method to continuously monitor an instrument, all right. So then for that reason, we use a photoelectric instrument, for example, like calibration or gyroscope or navigational instruments, right? Or laser instrument. Laser is just an acronym, so LASER with the dots, right? But then we get rid of all the dots. No, so instead of L dot, A dot, S dot, E dot, R dot, we're now reading it just laser like a word, yeah? It's just an acronym for light, again, amplification, right? By, S is for simulated, and E is for emission, okay? And R is your radiation, right? So we're going to simulate and we're going to emit a radiation and we're using the light amplification, and we call that laser. So it's produced by applying light to a solid or gas, okay? So that is excited. We're going to energize that. Excited means just energized or energized state. Why do you have to excite? Because you want movement, okay? So really highly energized. So that's why they go real fast. And under proper condition, an intense narrow beam of single color light, okay, results. So every time you want something to move, temperature, the same thing. So atmosphere got all kinds of molecules right in the nitrogen coating on the side, oxygen, water vapor, everything. Okay, they can condense. All right. So you have a warm weather is because we're making these molecules move all the time. So as soon as that, okay, uh, energized states is going down, you feel cold. The temperature go down, meaning they're not moving. Okay, as much as they were before. So that's why you feel cold temperature. Okay, when they condense down, it's gonna come down like water. If that's water, come down like rain or snow. Okay, even hail. Okay, all of that is just you're dealing with the movement of these little things right in the atmosphere. So now we're gonna do the same principle in your light. So light molecules are smaller than what we have, right, in the atmosphere. So here you're going to see a smaller, like photons. You're dealing with the photons, electrons, and the neutron state. Okay. So anyways, photo. So lasers, we're dealing with the beam, light particles, right? So we want it in a very energetic state. So we're going to apply the light, okay, to the solid or the gas, right? And we are energizing that solid or gas, applying the light onto it, and then under proper condition, an intense narrow beam of single color light is going to come out, very pushing out. So the first successful laser we use ruby, okay, because ruby is just to make sure that the wear doesn't happen, okay, quickly. So laser should not be looked directly by human eye. You shouldn't be doing it because it's going to damage your eyes. So laser beam is again unlimited in length, okay, go all the way to infinity and can be used in metrology. So therefore it's a very powerful and useful, okay, thing in metrology that we use for measurement. So the line of sight beam can be seen conveniently, all right, with the laser instruments. So this is another very powerful application of human, okay, endeavor by using our knowledge from education, right? Laser using playing with the lights, and we're controlling the lights in the way we want it. Okay, how do we control it? We design the instrument, and then we're going to make the light gold, okay, and use it to energize a state of a solid or a gas to produce a laser beam. And we're going to use the beam that produced out of that instrument, okay, to measure, yeah, the length that we want to measure. All right, laser light. So getting into physics again, so laser lights today produced by continuous wave, all right? We call that the plasma tube, and plasma tube looks like that, okay? So laser beam consists of light with one wavelength, okay? You have many different wavelengths, we already learned that, okay? And all the waves are in the phase again with each other, in phase, okay? The in phase, we have one single wave dealing with laser. Okay, and we use a plasma tube. Okay, it looks like this little shining thing right there. Okay, so laser instrument, coming back the same thing, alignment, alignment, and alignment. So a laser alignment instrument is constructed just like the conventional laser instrument. So all parts are inside a precisely machined barrel. And it looks like a little barrel like that. Okay. And the laser beam, again, the line of sight, your LOS, is precisely centered, okay, on and parallel to the axis of your barrel. And then supports, again, are used with your laser instrument for alignment. So when you look at this complicated diagram, okay, you don't have to go into it, just try to look at it. So externally, you can see the laser instrument resemble the line outside. It looks like a telescope, yeah. Internally, the only resemblance is the important one. Okay, both they have optical axis optical axis exactly in line with the mechanical axis of their barrels. Yeah. So here, when you get into here, you're going to see the beam right there. Yeah. And you don't need these screws and all kinds of stuff right there. Okay. All you have to understand right there, we need this. Okay. Objective lens is right here. And this is your laser plasma tube right there, and we're using gas here, and that's your helium and neon. Okay, so this is a very powerful active medium, dangerous medium, but then that's how we produce the laser inside of this barrel. And here you can see important another piece is your mirror, okay, to direct the beam. Okay, equipment. So equipment consists of basic elements in laser instrument. So laser instrument and then your support. Support again is for alignment and a quick setup. So laser needs a greater amount of power, okay, to operate because you have to energize the solid or gas. And the amount of heat every time you have to do the energizing of a solid or a gas. So you're doing again, I'm moving my little fluor particle right there again. Okay, you're moving that, okay, inside of your solid state or gas state. Okay, so every time you move, temperature go up. Every time there's a temperature, there's a transfer of, okay, heat. Heat is nothing but it's a transfer. Okay, we call it heat. That means that the transfer of energy is happening right there in these moving energized particles. Okay, so the amount of heat again will come all dissipated. Okay, must be paid close attention. So heat is a issue, okay, in laser instrument right there because they always come out. Why there's heat? Because we're dealing with a very highly energized state, okay, of either a solid or a gas in that plasma tube right there. So the laser instrument has no eyepiece, okay, as laser cannot be again directly seen by human eye. So, but the beam can be safely seen, just the beam, okay, in the ambient light. You have to have a light setting. Okay, alignment. So laser alignment instrument can be used like alignment telescope because we're just trying to find as straight as possible the line is by using these instruments. So photoelectric sensors, we use them again in this instrument, okay, by specialized target. One type is called the quad cell target to define the alignment. The quad cell target, just a target to make the alignment is just a one cell, all right, in each quadrant. So that's why you get this name quad. Yeah, it's your quad, yeah. And detects the changes in light intensity on it. Okay, that's why we call that the quad cell target. The target, okay, doing again, your laser alignment instrument is to align, all right? So therefore you need the target to get the to define the alignment. Okay, see-through targets. So here you see the quad cell detector target right there, right? And this is your beam, your laser instrument right here, and this is your see-through detector target. So the see-through targets can be used to determine displacement, all right, from a reference, which is your laser line of sight here, by placing them along it. So see-through target here, okay, may be placed along and establish, all right, a laser line of sight and displacement from that reference can be determined. Okay, auto collimation row. I put it there because it's so boring. Look at that, so cute. Okay, so auto collimation displacements are angular. So that's here in this example 63 seconds of arc for auto collimation that we normally use. So one commonly used auto collimation, all right, arc is nothing but just an angle measurement. So it's just called a commonly used auto-collimation accessory is a laser beam finder screen. Okay, it's just a accessory and it's just a finder screen to be able to see. And then the return beam can be quickly located with a screen for alignment to the line of sight. So here, auto-collimation row is just attachment. Okay, they're just trying to kind of enhance, okay, your screen. So therefore we add the laser beam finder screen, right? So you can be able to locate as quickly as possible the return beam. So where does the return beam, okay, come? So it's from your line of sight, okay? And you're doing the screen alignment with it. Okay, advantages. So this is our last slide. Advantages for photoelectric sensors. Okay, these are the sensor inside of instruments. They're not that big, by the way. It's an exaggerated picture. So they're used in place I for conventional optical alignment instruments, and the increase of precision, and then provide the ease of setup. Yeah. So the benefits of laser are hard copy records, remote readout, continuous monitoring, multiple viewers, and vision errors. Okay, so that's it for the very big chapter 16. Make sure you take it in slowly, okay, and go slowly. I'm not throwing on too many assignments right there, but it's good for your knowledge. So we're gonna throw, okay, little by little, and we still have about 4 weeks to final.